In this video, we are presenting AWT, a novel initialization method for class-incremental semantic segmentation. It is a joint work between the German Research Center for Artificial Intelligence, the Birla Institute of Technology and Science in India, and the Computer Vision Center in Barcelona, Spain. Let me briefly introduce what class-incremental learning is. In the field of continual learning, a model is not just trained once, but continues to learn new concepts throughout its life cycle. When the task at hand is semantic segmentation and the newly introduced knowledge is additional semantic classes, we speak of class-incremental semantic segmentation. If this problem is approached in a naive way, simply by a sequential training of different sets of classes, the model will completely forget its previous knowledge. This phenomenon is called catastrophic forgetting. There are different strategies to encounter catastrophic forgetting, but in all, there is always a trade-off between the plasticity and stability of the model. That is, the ability of the model to learn new classes and remember the old ones. One important aspect in the plasticity-stability dilemma of class-incremental semantic segmentation is the initialization of the classifier for new classes. Once new classes are exposed to the model, the classification layer needs to be extended with new nodes. This extension of the network architecture introduces new trainable weights, of which the initialization is crucial. Because better initialization leads to faster learning of the increment, the network is less prone to forget during this process. The other way around, the initialization allows the network to use the previous knowledge and build on top of it. Newly emerging classes have previously been trained to be part of the background. That's why in state of the art, the new extended classifier is initialized with the weights of the background class in the previous step. While the assumption behind this strategy is more than reasonable, there are practical limitations. Due to the transfer of identical weights, distinct classes now share the exact same feature representation, which results in confusion and concurrent learning of these classes. Here is our solution to the aforementioned problem. Instead of transferring all weights of the background classifier to the new classifier, we select and transfer the most relevant weights only. Naturally, not all features contribute equally to the classification of all classes. Even within the same class, some features show higher relevance for certain areas of the image. By computing the attribution of features in areas where new classes are present, we can identify the most relevant features for the classification of the new classes. This is shown, for example, in the two attribution maps at the top, in which one clearly overlaps with the mask of newly introduced classes. We average over all samples of the dataset for the current task to find the most relevant features for the new classes. Those are the features we transfer to initialize the new classifier. Because we use attribution to select which weights should be transferred, we call our initialization attribution-aware weight transfer, AWT. Due to the meaningful selection of features, the conflict in incremental learning is reduced and plasticity is significantly improved at a reduced cost of stability. Let's have a look at some of our results. In this diagram, we show the relative improvement of our AWT over a baseline approach, MIB. In total, 10 different experiments and 3 distinct datasets are shown. In all of these, our proposed initialization improves the results after incremental training. In many cases, the relative improvement is around 10%, and in one case, the mean mIoU is almost doubled. Please note the logarithmic scale. We can further observe that AWT shows less improvement in experience with only one increment, for example, the first columns for VOC and ADE, but is especially suited for larger incremental sequences. In fact, by using the proposed initialization on top of previous methods, we achieve state-of-the-art results in 9 out of these 10 settings. Implementation details and much more experiments are provided in the paper. If our initialization strategy has caught your interest, please consider reading our paper. Thank you for the attention.